Hydrogeology is the study of water in the geologic system. Now, in general, we're interested in water in the overall Earth system, but hydrogeology tends to focus on groundwater. Now, groundwater interacts with surface water, and that'll be important for a variety of applications, but the overall focus will be on water in the subsurface. Now, there are a variety of reasons why we're interested in that. Water interacts with a variety of geologic processes, so to understand this system, we need to understand the role that water is playing. There are also a variety of important practical applications. Water is one of our most important resources, so we need to access groundwater to use it for irrigation or drinking water or perhaps industrial purposes. So water supply is an important application. And we also want to protect the quality of groundwater. So contaminants like this stuff here we're concerned about, and we want to understand how those contaminants contribute to the contamination of groundwater and how we might clean them up. So the variety of activities that hydrogeologists do to pursue understanding water in the natural system. Here are some folks doing a field assessment, and there's a drill rig nearby. This is a drill core right here, and they're taking subsamples from that material and storing them in vials for later analysis. The field activities lead to data. Data is combined and analyzed, in some cases using theoretical models. Here is a model of a plume. There was a source right here, and this is the subsurface, and you can see the plume is headed down in that direction. Each one of these blue dots is one of the samples similar to what's being obtained here. So we get this three-dimensional structure that forms this groundwater plume. And so understanding how the plume moves and ultimately what might be done to stop the plume or destroy the contaminants in place, those are some important applications for hydrogeology. So one of the big organizing principles in hydrogeology is the hydrologic cycle or the water cycle. Here's a graphic from the USGS, and I'd recommend going to their site for more information about the hydrologic cycle and really about many things related to hydrogeology. So the cycle here that really allows water to move at the surface of the earth involves energy input from the sun. That energy evaporates water and allows or enables the transformation from liquid to a vapor phase. And that's important because the vapor can rise and move over land where it falls as rain or snow, and it gains elevation. And then from here, once the water reaches the ground surface again, it has gravitational potential that allows it to flow through the subsurface or over the surface, or some combination of both, and then ultimately returning back to the ocean. And there are a variety of processes that happen along the way, as you can see from this diagram. So to keep with the focus on groundwater, we should get a first look at the groundwater flow system. So this is just a basic look, and we see some important components. So what happens here is that rainfall, shown with these clouds, falls on the ground surface, and some of that rain infiltrates and goes down and reaches this dotted line here. This dotted surface is the water table. So water is infiltrating, it reaches the water table, and then it flows along the paths that are shown here. These are groundwater flow paths, and the water is flowing from a recharge area here in the uplands through the subsurface and then discharging to this nearby stream. So this system where local recharge is discharging to the nearest stream is called a local flow system. This is an unconfined aquifer, and this is a common and very simple groundwater system. we see that there's a groundwater divide right here. So water on this side of the divide is flowing towards that stream. Water on the other side is flowing to that stream. The water table is indicating the direction of flow. So the slope of the water table gives us a flow direction like so. And right up here at the divide, the slope of the water table is 0. So we'll step through the events that occur during a rainfall, an infiltration, and evaporation event. So this is a small snapshot of the overall hydrologic cycle, but one that will point out some important events and processes and allow us to hit on a few terms that we'll be using throughout the next few weeks. And so just in order to get on the same page, let's take a look at this graphic. So we've got a cross-section here. This is showing an unconfined aquifer, very much like what we saw in the previous slide. The aquifer down here, we've got the vadose zone above. The water table is shown by the black line, and this little triangle is a symbol that is used commonly to represent the water table. So the way that we can know that that's the water table is because the pressure here is equal to atmospheric or 0. Often we'll use atmospheric pressure as the baseline. The water table is the surface where pressure equals 0. And then up in the vadose zone, what I've done is to show the soil B horizon right here. And the B horizon is a layer that's common in many soils where clay has accumulated, and it causes the hydraulic conductivity there to be lower than it is above, and also in some cases below the B horizon. So with those terms in mind, we'll get rid of them, and then I'm going to erase this writing that I've done, and we'll go through this rainfall cycle. So we start here with some rain, and the first thing that happens to that rain is that in our scenario here, there's some trees, and the rain lands on the leaves of the trees, and that rain it is intercepted by the leaves, and it never reaches the ground surface. So this will be important because this water will never get into the subsurface, and so it'll never really be in play in the hydrologic cycle that we're interested in, that will involve interaction with the subsurface material. So the intercepted water is going to be kind of held out of play from the cycle, but with continued rainfall, the rain makes it through the trees, reaches the ground surface, and starts to infiltrate. So we have this little surface layer here where water is infiltrating. And by this term, infiltration, I mean water that is crossing the ground surface. So that happens fairly early in the rainfall, and then with continued rain, this zone above the B horizon increases in saturation, and the water is moving downward. It reaches this lower permeability zone, the B horizon, and that causes the saturation to increase, and then that gives rise to downslope flow. And so the flow is going downslope, but it's going in the subsurface. So you really don't see this happening. It's going over this low permeability zone in the subsurface, and this process is called interflow. Another term for it is subsurface storm flow, because it's happening during the rainstorm. And this is important because this water going downslope can cause the flow to reach the stream fairly quickly and cause the water level in the stream to rise. Now, with continued rain, what happens is the saturation here in the soil increases, and at some point the saturation at the ground surface will be complete. The soil will be saturated, and in that case the water will run across the surface of the soil. it'll run downslope, and it'll flow much more rapidly than it did when interflow was taking place. So this is called overland flow, and overland flow allows rainfall to be shed off of the landscape much more quickly than interflow, and so it reaches the stream quickly and enables the water to rise in the stream quickly. And so this is a process, the overland flow and storm flow really lumped together in a process that we think of as storm flow. Those things are going to be what causes floods. So if we're interested in streams rises rapidly, we're interested in the storm flow process. The rain is stopping, and what I'm showing here is that we recognize that this B horizon, the permeability is lower than it is above in the A horizon, but it still has some permeability and the water is flowing through it. So some water makes it through the B horizon and flows down through the vadose and reaches the water table. And that'll be important because that's adding water to the aquifer. This is a process called recharge, and when we add water to the aquifer, the water table will rise. So there's the water rising up. We've increased the storage of water in the water table. So what's happening during this whole process is that groundwater is flowing from upland areas where the recharge has occurred to the stream. This is essentially the same process that we saw in the previous slide, and that it is happening here. We've got the water table right here, and here's where the slope is 0, so this is a groundwater divide, and we can see flow going from upland areas to the stream. So the rain stops and the sun comes out. And now evaporation will take place, and the first thing that's going to evaporate is this water that has accumulated during the rainfall and has been intercepted on the leaves of the trees. The intercepted water evaporates off, and now the trees are becoming active, and they say, well, I need to get some water to transpire and do my biological processes. And so the trees have roots down here in this area, maybe going down into the B horizon, and so they're pulling this water that's been added to storage at shallow depths from the rainfall. They're pulling it back out. This water flows up the trunk and goes out through the leaves and evaporates at the leaves of the trees, and this is quite an effective process at pulling water out of shallow depths in the soil. So this is a process where it's evaporation, but it's really the biological process of the trees that are contributing in a very important way. It's much more effective than just straight evaporation off of the ground surface at removing water from the shallow depth. So we call this evapotranspiration. It's kind of a long, cumbersome word, so ET is often the abbreviation that we'll use for that. What's going to happen now is the evapotranspiration process is ongoing, but I want to go and focus on the water table and what's happening there, because this process of flow that's being shown here is ongoing. There's water flowing in the stream, even though maybe it's been quite a long time since it's rained. There's water flowing in the stream, and that's because the groundwater is discharging up through the stream bed. And in order to do that, the water has to come from somewhere, and indeed, it's coming from storage in the aquifer. And so for this process here to take place, for the water to be discharging to the stream, it has to be removed from storage up here in the aquifer, and that causes the water table to fall. And so the water is coming out of storage in the aquifer and providing what we'll call base flow to the stream. This is groundwater discharging up through the stream bed and giving a base level of flow to the stream. The other component of flow in the stream is from storm flow. But we know that streams are flowing quite well in between storms, and that's because of this base flow process. What happens then is the process of evapotranspiration is removing water that's been stored here at shallow depths, and base flow is causing this water that's stored in the aquifer to go and discharge to streams. And those processes continue until the next rainfall. The next rainfall then acts like a pulse, relatively short duration, that puts water into storage in the shallow vadose for access by the plants, and also some water is migrating downward, reaching the water table as recharge, and then ultimately flowing to the streams where it discharges as base flow. Various terms that I've been using are important to know. I've given you a handout, and the terms are summarized there. So hopefully you can come up to speed with these terms if some of them are unfamiliar. There's another handout that looks like this, and it describes some of the basic processes, again also with some of the basic terms that we'll be using in the course. So take a look at those handouts and review the terminology. Or another process that overarches all of hydrogeology, and it will come up many times in what we do, is the water balance. This is really a specification of the conservation of mass principle from physics. It allows us to solve a variety of problems in hydrogeology. It also allows us to think about our data in important ways. So it's really fairly straightforward. To apply the water balance, we need to first identify a region over which we'll take the balance. This dashed line is our region. Often we call it a control volume. And so that's step one. Identify the control volume. And then step two is to identify the flow rate coming in. So I use this capital Q to mean volumetric flow, so volume per time. So Q in is the volumetric flow rate into this volume, and we also have a volumetric flow rate out. And so the third thing that we need to consider is the volume of water that's stored in the control volume. If we recognize that if the flow rate coming in, if this flow exceeds that flow, then we have water accumulating in the control volume, and the water level would rise, like so. And so we are interested then in the rate of change of this water stored in the control volume. So there's a delta. I'll use that to mean change. So this term here is the change in the volume stored. And if we're interested in the change in the volume stored in a unit of time, then we get this thing here, which is the rate of change of the volume stored. So we can put this together and come up with the overall balance, where we say that the flow rate in is equal to the volumetric flow rate out plus the rate of change of storage in the control volume. So this will have a variety of applications. We'll use it many times. And just to see a quick application here, we can go back to the cross-section that we saw, where we've got a variety of different terms here. Evapotranspiration, you see, and precipitation, and groundwater flow, and recharge, and so on. And so to apply the water balance, we go through these steps. And the first one is to say, well, we've got to apply a control volume. And so the way that you do that, it really depends on the problem that you need to solve. So what I'm going to do is say we have a problem where we need to do a water balance on the aquifer. So the strategy then will be to apply the control volume to the aquifer. And there are a couple of ways that we can do that, but let's just say, for an example, that we say that the control volume is right there. And if we do that, then that's the first step. That's our control volume. And the next step then is to determine the fluxes that cross the control volume. And we need to do that just by looking at our sketch. And from our sketch, I think we can see that we have some groundwater that's flowing out here. So that's what's shown in our sketch. We have some water that's flowing in here. The recharge is flowing in. And we've got some base flow coming out. I guess also in this sketch we've got this guy here. This is riparian evapotranspiration. The riparian zone is the zone that's down next to the stream, and riparian evapotranspiration is distinct from this regular evapotranspiration because these guys here, and you'll notice this on the handout that I have a little sketch of a willow tree here. And so willows put their roots down and are able to pull water out of the saturated zone. The plants up here, regular trees, aren't able to get down to the saturated zone, to the water table. They just pull water out of the relatively shallow veda zone. So these guys here, the riparian evapotranspiration, they can access the saturated zone. So we would include the riparian evapotranspiration here in the balance. So if we, at least at this point, ignore any kind of changes in storage, then that last term in the water balance is 0. And we can write the balance as the flow rate in, which would be the only thing that's coming in here is the recharge. So we would have recharge coming in, and then the things that are going out would be the groundwater going out, and the base flow going out. And we also have the riparian evapotranspiration going out. So that would be an application of the water balance principle applied to an aquifer. We'll pick up this idea of using a water balance to set up problems in more detail later on. But this is just an introduction here to get you started thinking about this important process.